Far beyond the outer planets, in the deep and silent darkness of space, a decades-old machine continues to communicate with Earth. Built with technology from the 1970s, it carries less computing power than even the simplest modern devices. Its signal is incredibly weak, yet it still manages to send information across unimaginable distances. After nearly half a century, Voyager 2 remains active in a region no one originally expected it to reach. What makes its journey remarkable is not only its survival, but the discoveries it has made. Scientists once believed there would be a clear and dramatic boundary marking the end of our solar system. Instead, the data revealed something far more complex and unexpected. The mission itself began during a rare planetary alignment in the late 1970s. At that time, the outer planets lined up in such a way that a spacecraft could use their gravity to gain speed and travel farther than ever before. Taking advantage of this opportunity, NASA launched two spacecraft in 1977, Voyager 1 and Voyager 2. Originally designed to last only a few years, both missions exceeded all expectations. Voyager 2 traveled past Jupiter and Saturn, then continued on to become the only spacecraft to visit Uranus and Neptune. After completing its planetary tour, it continued outward into uncharted space. Eventually, it approached the outer edge of the Sun's influence, a vast region known as the heliosphere. This enormous bubble, formed by solar wind and magnetic fields, surrounds all the planets and acts as a protective shield against interstellar radiation. Scientists expected a clear boundary at its edge, called the heliopause. According to earlier predictions, crossing this boundary should have been obvious. There should have been a sharp change in particle activity and a noticeable shift in the direction of the magnetic field. But when Voyager 1 first crossed this region in 2012, the results were confusing. Then Voyager 2 reached it in 2018 and confirmed the same mystery. The expected dramatic changes did not appear in the way scientists had imagined. While some indicators shifted, the magnetic field did not flip as clearly as predicted. Instead of a sharp dividing line, the boundary seemed blurred and complex. This suggests that the edge of our solar system is not a simple border. It behaves more like a transition zone, where solar and interstellar forces mix and interact. Rather than a clean separation, there appears to be turbulence and overlap, making it difficult to define exactly where one region ends and another begins. Further analysis raised even more questions. The size and shape of the heliosphere were expected to change depending on solar activity. Yet both Voyager spacecraft crossed the boundary at similar distances, despite different solar conditions at the time. This challenges existing models and suggests that the structure of this protective bubble may be far more dynamic and unpredictable than previously thought. Meanwhile, Voyager 2 continues its journey under extreme conditions. Powered by a slowly decaying energy source, it loses a small amount of power each year. Engineers have had to shut down non-essential systems to keep it functioning. Despite these limitations, it still transmits valuable data from billions of miles away. At some point, the spacecraft will no longer be able to operate. Its signals will stop, and communication with Earth will end. However, the probe itself will continue drifting through interstellar space for countless years. Its mission has already changed our understanding of the solar system. What it revealed is simple, yet profound. The boundary we once believed was clear and well-defined is anything but. The true structure of our cosmic neighborhood remains more mysterious than expected, reminding us that even after decades of exploration, there is still much we do not fully understand. Even after crossing the boundary of the Sun's influence, the journey of Voyager 2 did not become simpler or quieter in terms of discovery. In fact, it became even more mysterious. Because beyond that invisible edge, the spacecraft entered a region that scientists had only theorized about but never directly explored before. This is interstellar space, the vast expanse between stars, filled with particles, magnetic fields, and radiation that originate far beyond our solar system. Before Voyager reached this region, many researchers imagined it as relatively uniform and calm compared to the dynamic environment near the Sun. But the data told a different story. Instead of a smooth transition, Voyager 2 detected variations in plasma density, shifts in particle energy, and subtle fluctuations in magnetic fields that suggested this region is far more active than expected. One of the most surprising findings was the increase in cosmic rays. These are high-energy particles that travel through space at nearly the speed of light, often originating from distant supernova explosions. As Voyager 2 moved farther away from the Sun's protective influence, the number of these particles increased significantly. This confirmed that the heliosphere does act as a kind of shield, reducing the intensity of cosmic radiation that reaches the inner planets, including Earth. But even this discovery came with complications. The rise in cosmic rays was not perfectly steady. There were variations, sudden changes that hinted at invisible structures or waves passing through interstellar space. It suggested that this region is not empty or still, but filled with motion and hidden activity. Another unexpected observation involved temperature. Based on earlier models, scientists predicted that the region beyond the heliopause would be extremely cold and relatively simple in structure. However, Voyager 2's instruments detected plasma temperatures that were higher than expected. This raised new questions about how energy is transferred and distributed in interstellar space. Some researchers began to consider the possibility that shockwaves or interactions between solar and interstellar material might be creating pockets of heating. Others suggested that magnetic turbulence could be playing a larger role than previously thought. Either way, the data indicated that this region is not as straightforward as once believed. Communication itself became a challenge as the spacecraft moved farther away. Signals from Voyager 2 take many hours to reach Earth, traveling at the speed of light across billions of kilometers. The farther it goes, the weaker the signal becomes. Massive antennas on Earth, coordinated by networks like the Deep Space Network, are required just to detect its faint transmissions. Despite this, the spacecraft continues to send back data, bit by bit, like a distant whisper from the edge of human reach. Engineers must carefully manage its remaining power, deciding which instruments can stay on and which must be turned off to conserve energy. Every decision is critical, because once a system is shut down, it is rarely turned back on. What makes this even more remarkable is that Voyager 2 was never designed for such a long mission. Its systems have endured extreme cold, radiation, and the slow degradation of time. And yet, it continues to function, providing insights that no modern spacecraft has yet replaced. As scientists analyze the incoming data, they are beginning to rethink long-standing assumptions about how our solar system interacts with the rest of the galaxy. The idea of a simple boundary has been replaced with something more complex, more dynamic, and less predictable. There is also a deeper implication to these findings. If the boundary of our own solar system is this complicated, what does that mean for other star systems? Do they also have irregular, shifting edges? Are their protective bubbles stronger or weaker? And how might that affect the potential for life in those systems?